Welcome everyone. So we are going to discuss today logic synthesis. So in today's discussion, we will talk about logic synthesis in basics, and then we will talk about specifically two kind of optimization, what is called two level optimizations and multi-level optimizations. So if you look into this VLSI design cycle, which we have discussed in our module 1, that we start from our initial system specification, and then we have some architectural design, and then we have say this specification of the of your behavior, and then we do high level synthesis, right. So here you have some architectural design which we can represent by C, C++, and then we convert this through high level synthesis to RTL, right, which is called register transfer level design. And then the steps come logic synthesis. In logic synthesis, what we does, we take this RTL and we convert to this gate level design, right, gate level. We just convert this RTL into gate level design, and then we will do physical synthesis, fabrication and packaging. So today's discussion topic is this logic synthesis. So what we does here, we just take some RTL, register transfer level design, which may be generated through high level synthesis, or some designer can write the RTL directly as well, right. And this logic synthesis tool which take this RTL and convert them to equivalent gate level design, right. So if you look into this translation, this from RTL to gate level, which is basically very obvious, right. I mean, there is nothing, there is no much complexity is there. For example, suppose in your RTL there might be some multiplexers, right. So you might have some marks here, which is basically taking say 4 inputs, and then we have say select line of 2 bits S0 and S1, which select this inputs this D0, D1, D2 and D3 based on this select value, right. So this is one marks in your RTL, but you can actually replace this marks by equivalent gate level design, where this is that equivalent gate level design, right. So here we have this selections based on this select line and the inputs, and then there is a OR, right. Similarly, suppose you have a full adder, right. So you just do adding to there may be some full adder which just take input A and B, and there is some carry input C, and doing this A plus B, right, and some carry out, right. So we can replace this RTL module by the equivalent gate level design. Yes, this is a full adder circuit. This is for 1 bit, and if you have this say 16 bit or 32 bit, that will be just chained, right. This will be the same block will be chained, I mean just as the carry input, right. So is basically the concept here is that in logic synthesis, when you try to convert this RTL to its equivalent gate level, we can just replace those block by block, right, marks by its equivalent gate level implementation, or say there is a adder its equivalent gate level implementation, there is a multiplier its equivalent gate level implementation, and so on. So there is nothing much complexity is there, right. So what is description here, this translation is kind of pretty obvious, right. So we have this RTL description and we convert it to gate level through this one-to-one mapping of this block to its equivalent gate level implementation. But what is important here is that this optimization. So once whatever the gate level the design you are going to get it, that may not be optimum, right. So then we have to apply lot of logic optimization technique just to reduce the number of gate, because if we just replace all this module by its equivalent gate level design, those implementation will be very much optimized, and there will be lot of redundancies, right. So the primary objective of this logic synthesis is this logic optimization. When you talk about this logic synthesis, we primarily talk about this logic optimizations, because now we talk about we have this unoptimized gate level design we have, and we have to apply such kind of optimization such that we can reduce the overall size of a design. That means the number of gates, or maybe number, I mean the total timing delay. So there might be different kind of optimization goal, but overall this main primary objective of logic synthesis is to this logic optimization, right. So in this logic optimization also have two type of optimization. One is called tech independent, and that is second was tech dependent, technology dependent, and another one is technology independent. So we will talk about this technology independent optimization today. So in technology independent optimization, what we do, we just think about that we have that library of gates are there, maybe we have only AND gates or OR gate, and we try to replace the whole thing using those equivalent gate, right. For example, say maybe you have only say NAND gate, right, or NAND and NOT. So you try to replace whole your design using only NAND and NOT gate and so on, right. So that is, and then we try to do all this optimization without looking into the actual technology dependency. Technology when your target architecture, right. Your target architecture may be say FPGA or ASIC and also we are not going to consider about those technology dependent thing in the technology independent thing. But in technology dependence, for example, say FPGA, we have say LUTs, if you have DSPs, if you have say RAM block RAMs. So when you are talking about those mapping or optimization, we try to map those AND gates, OR gates and AND gates to that LUTs, right, because those are the technology unit of that particular FPGA. So the idea is that we have kind of two steps. One, first we try to optimize without considering the target architecture, target devices. We make it independent of the technology, target technology, and then we do this technology dependent optimizations. Okay. So today we are going to primarily discuss on this independent part, and there are primary two kind of optimization is important in this technology dependent. One is called two level logic optimizations and the second one is multi-level optimizations, multi-level logic optimization, right. So if you just think about this logic optimization steps, what is our input? We have a Boolean network. So that means the circuit in terms of Boolean gates, and we have some timing characterization of these modules, right. So for each module what is the kind of delay and all those informations, and then we try to minimize the area, right. We try to minimize the area of this overall circuit, the Boolean network, which actually meet the timing constant. That is the overall objective here, right. So and we will talk about this two level and multi level logic optimization in this context, right. So what is two level combinational optimizations, logic optimization? So in the two level combinational logic optimizations, we represent these Boolean formulas as a sum of product form, right. So we have set of product terms and then we have the summation of this. So this product is basically AND gate, right. So we have this, that means in the logic level we have two levels, two layers. So in one plane we have the AND gates, set of AND gates, and in the next level we have the OR gates, right. So this product, so basically if you just think about say A B C plus A B D dash plus A B C D dash and so on, right. So these are the product terms, right, and this is sum of product. So this product is basically nothing but the AND of these inputs, right. So this is this AND plane, we have this say A B C, here A B D dash and so on, right, and in the OR plane we are going to have the OR of all this, right. So this is basically two level of representations, right. I have AND level and then followed by the OR level, right. So the idea is that in two level optimizations we always represent those Boolean formula in this sum of product form. That means we have all the products and then we have a summation or the OR gates, and we try to optimize the circuit in this in these representations. Just to explain this two level logic optimization in more clearly. So we have the set of inputs and they have and their complement, and this is the AND plane. So these are kind of product term, right. So this is one product, this is one product, this is one product, this is one product and on. Let us say here some of them may be one, right, some of them will be taken care of, and then in the OR plane some of the product will be important for this output, right. For this output there may be some product is important, right, and so on. It is clearly mentioned here. So for example, here I have three inputs, so A, B, three inputs. So they are complement, there are total 6 input lines, and this each row represent one product term, right. So for example, this product we have A and we have B bar, right. So this is basically representing A B bar, right, and this is basically B and C, right. So this represent B C and so on. So each row of that particular plane is representing one product term, and now this particular output, this is the OR gate. So now it may not take all the products. So there are say 6 products here, 1 2 3 4 5 product terms are here, and this is taking only these 2 product terms, right. So this F1 is effectively means A B bar plus B C, right. So F2 is basically taking this product term and this product term and so on, right. So this way I can represent my overall circuit in these two representations. So it is basically called programmable logic array when we have this AND plane and OR plane. And what is the optimization goal here? We try to reduce the number of row, right. We try to reduce the number of products, because if you have number of row is less, then the size will be less, right. Similarly, I want to reduce the number of column as well, that means the number of input literals, right. So, this A dash all this kind of call is literals. So, the objective here is that to reduce the number of product terms, that means if we have number of row is less, that means the number of AND gate will be less, is effectively meaning the number of AND gate will be less. So, it will have a less area, and then also if possible the minimize the number of input gates. Sometime we try to, instead of this all 6, maybe in some scenario I do not need this particular column, right, or in some scenario I do not need this particular row. So, this is how we can actually optimize the 2 level circuit, right. So, on the other hand, in a multi level, in here you can see there are only 2 levels, right. So, in multi level we can have multiple levels of gates, right, it is not only 2 levels. So, and in multi level optimization we try to do not consider our representation just in 2 level, we can have multiple levels of gates and we try to optimize the whole circuit in that mode, right. So, why this 2 level computational logic optimization is important? Because when it actually means of optimizing the implementation of circuit that are direct translation of the 2 level tabular form, right. So, this is how we actually visualize our circuit, right. So, this is, and it has also have a very one-to-one corresponding to this PLS. So, for PLA optimizations this 2 level optimization is important, and although for multi level, even for this 2 level optimization is also important, because that this 2 level optimization is a key important factor for multi level logic implementation also, right. So, basically this when we are talking about this multi level optimizations, we effectively in the background we each component is represented as a 2 level function. So, it is important to understand this 2 level optimization, logic optimization as well. Okay. So, but as I mentioned, this is something is not kind of scalable 2 level optimization, right. For example, there are too many too expensive to implement a 2 level form, right. In some time this function cannot be represented in 2 level form. For example, this you just think about the example of the 16-bit adder. So, in the 16-bit adder there are 32 input lines, right. So, there are 2 inputs. So, 16-bit 32 bits, and then we have 2 to the power 16 product terms, and then you are going to select some of them, right. So, it is basically understand just for adder we have 2 to the power 16 number of product terms, it is too costly sometime, right. So, we may not have the efficient implementation 2 level implementation of all functions sometime, right. So, that is why we try to we actually represent the Boolean circuits using multi-level computational circuit, using multi-level computational circuit, right. And also sometime if we represent it as multi-level, we can have we can actually optimize the overall circuit as well. Just to give an example here, you can see here there are 2 functions and they are like this, right. So, there are 6 product terms and we cannot optimize any of them, right. So, I need 6 product terms. So, 6 AND gate and the 2 OR gate to just to represent this. But in multi-level what you can see that there is a common terms here is A, right. So, we can represent this as basically A into B plus C, right, plus AD, and F2 can be represented as this A bar into B plus C plus A, right. So, I can see there is a common term, right. So, now if I represent in 3 level, so I can compute this B plus C first, right, this is my B plus C, and then I can do this F1 is basically nothing but this is K. So, A K plus A D, right, and this is A dash K plus A, right. Now, I can do this. So, instead of just having this, so this is basically if you just think about the actual implementation, I have in 2 level I have this A B A C, A B A C and A D, and I have this is my say F1, right, and similarly I have these 3 terms for F2, right. I can have this. So, on the other hand here what I can do, I can just have this is my D, and now I have this AND gate to just do this. So, this is my K, right, this is what I just think about, this is K. So, this is my K and now this is A, and then I am just going to do this AE, and this is my orbit, right. This is how I can represent my F1. So, instead of this 2 level I have now 3 levels, right. Similarly, I can use the same K to represent the F1. So, when you have this multi level implementation, you can actually have this kind of common sub expressions which you can actually use for multiple functions, and that will give you more optimization, right. So, that is what is the advantage of multi-level optimization. So, we are going to learn both this 2-level combinational circuit optimizations and multi-level combinational circuit optimization today. Before going into that, we are going to discuss little bit about our basic knowledge of Boolean logic, because that will be useful when we are going to discuss about this 2-level logic optimizations and multi-level logic optimization. Okay. So, I mean, if you just think about the Boolean space, so if you have say n variable, we have 2 to the power n values, right. I mean, either this is 0 or 1, right. So, if you just think of the space, if you have only one variable, one Boolean variable, either this is 0 or 1, right. If you have 2 variables, then we have sorry, this is 0 and 1, this is just true, right, this is true or false. This is one variable, then true or false. If it is say 2 variables, either one of them 0, so there will be 4 values, right. Similarly, if there are 3 variables, I have 8 possible values, right. So, I can represent this is kind of a hypergraph. Similarly, for 4 variable, I can represent either this kind of tabular form, or I can use a kind of a hypergraph, right. This is called hypergraph. So, this is how we can represent this Boolean space. And then what is Boolean function? It takes some n inputs, some function of say n Boolean variable 1 to n, and that map to 0 or 1, right. This is 0 or 1. So, this will be mapped to this. This is what is called Boolean function. So, it depends on all this it depends on all this n Boolean variable, and that function will map this to 0 or 1, right. So, now if we just think about the n input variable. So, we will say these variables x 1 x 2 to them is variables, and this x 1 x bar, x 1 bar, x 2 bar as the literals. So, this terminology is important. And also if so, if you, for example, if I just give an example for this f is basically what is saying this x 1 bar, x 2 bar, right, x 2 bar plus so basically what is trying to say is this. So, this function is saying that whenever this this value is x 1 bar and x 2 bar, then output is 0. If x 1 bar is 0 and x 2 is 1, then output is 1, and so on, right. So, x 2 1 is 1 and x 2 is 0, then output is 1, and both of them are is 1, then output is 0, right. So, I can represent this f is basically x 1 bar, x 2 and this, right. So, this one is the on term, right. So, this is x 1 and x 2 bar, right. So, this is what is the function. So, we will call this all these terms is called min terms, right. So, min terms is that is a product form where all the variables are present, right, either in true form or bar, I mean either complement or actual form. So, they are present, then we will say that these are min terms, right. So, if there are 2 variables, I have 4 possible values, right. So, there are 4 possible values here, and on terms is this when represented by red here, where if the function is 1, the on term is also be 1, right. So, for example, if this function is 1, this or this, if this is 1, sorry, in this, if this min term is 1, the function will be 1, right. That is what this sum of product means. So, if any of them is 1, the output will be 1. So, onset is those min terms which is basically 1, when the if that is 1, then the function will be output will be 1, right. And offset is what? The other one, right. So, this is offset, this is and this is and this is offset when the value is 0. So, I can represent them in the hypergraph like this, right. And we can also have some don't care, which we are going to discuss later. So, the idea is so key point here is that Boolean function taking n Boolean variables, map it to 0 to 1, that variables and the literals is that x variable or their complement form, and the onset is basically those min terms. Those are when there are 1, the function is 1, and the offset is when the function is 1, this is 0, definitely 0, right. So, that is what is we represent the Boolean function. And how do we represent this Boolean function? We usually use either hypergraph or say truth table, right. So, for example, here you can see here there are 3 variables, and this variable, so this point representing 0 0 0, that means x 1 bar, x 2 bar and x 3 bar. This point is representing x 1 bar, x 2 and x 3 and so on, right. So, this is how the hypergraph is represents, and here you can see that between 2 consecutive point, 2 adjacent point, there is only difference of 1 bit, right. For example, this point and this point, the only difference is between this bit. From this point to this point, there is the difference between this middle bit, right, and so on. So, this is how we can represent this, and here this this black dots are the onset and these greens are the offset. For example, this is onset, this is onset, this is onset and this is onset, right. This is how we can represent the thing. So, there are maybe various other options. This is one is truth table, one is sum of product or product of sum or binary decision tree, BDD binary decision diagram, Boolean formula or Boolean network, right. So, we can represent these functions in various form. Usually, I represent by this hypergraph or say truth table or say sum of product form or say binary decision diagram and all. So, there are various ways to represent these Boolean functions, right. Now, I will come to discuss what is cube, right. If you just represent my Boolean function as a this hypergraph, then each min term, right. So, min term is something what I just defined here is basically is a product term where all n variables present either in true or their complement form. For example, so there are 3 input variables say ABC, then ABC is a product term, ABC dash is product term, right. So, those are min terms, right. So, so in the cube this is also a product term, right, but that may not contain all the variables in their true or complement form. For example, if you just think about this x1 bar, x2 and x3, so this is that node. So, this is a product term and that is also a cube, right. And now, if you just think about I have only 2 variable, this will represent one these 2 things, right. So, this is what is x1 bar and x2. So, because this is x1 bar and x2, right, this is x2. Similarly, if you just think about my cube is only x1 bar, then it will represent the whole plane, right. This whole plane is represented by this, right. So, this is basically cube is also a kind of product term, but it may not contain all the literals, right. So, and if it is has less number of literal, it is actually covering more than one min term. So, in the hypergraph each node is kind of a min terms, right. So, all because in this point all the variable has either they have in true form or their complement form, and if we have a cube which is less number of variable, then it is actually covering more than one term. For example, if you have 1 less here, it is covering 2, there are 2 less here, 2 less variables are there, it is covering a one space itself, right. So, this is how we are going to represent, right. And now, this is important because the concept of implicant. What is implicant? When 2 or more terms may be combined to get a term of reduced size, that is covering that a function, right. So, for example, suppose I have a function ABC and ABC bar. So, an implicant of this is AB, because AB is basically ABC plus ABC bar. So, it is covering both of them, right. So, this cube is kind of an implicant. So, this cube either can be a min term or it can be implicant. For example, here this is an implicant because it is now covering 2 min terms. This is also an implicant because it is covering 4 min terms, right. So, it is basically we try to we have the min terms because min terms are the product terms, and that is actually if you represent your function is sum of product SOP form, then this min terms is the onset, right. Those min terms in the sum of product terms are there, those are the onset of the particular variable, and we try to find implicant which actually try to cover more than one min terms, right. That is what is something is called implicant. And then what is important here is a prime implicant. So, we try to grow, right. For example, if you have say these 4 variables are there, initially you might have min terms all 4, right. So, individually they are all min terms, right. Then you try to grow it for you cover a min terms or say implicant which cover only these 2, then you got another implicant which covering these 2. Then you can expand further, you got this min term x1 bar which will covering all these 4, right. Then this is called prime implicant, because now I am not able to grow further, because even if I grow it will not, because if we assume there are only 4 onset here, even if I grow then I am going to cover some offset, right. But that is not that is not correct, because our objective is this onset are important, because if those any of them is 1, the function will become 1. So, we will only bother about this onset, we will never try to cover any offset, because that will actually change the functionality of your of the function, right. So, the important point here is that we have the min terms which is the sum of this product form, then we try to find the implicant. Implicant is basically an product term which try to cover more than one min terms, and then we grow further and we got a saturation point which is called prime implicant, because I cannot try to reduce further number of variable there, so that I can cover any other new on term, right. If we try to grow further, it will cover some off term which is not correct. So, that is called primary implicant, as I explained in this diagram, right. And then there is a term called essential prime implicant. That means, if there is a prime implicant, is essential if it covers some min term which are not covered by others, right. You might have two prime implicant which have some subset, right. For example, suppose you have say one implicant is like this. So, let me just draw it here. So, suppose this is my onset here. So, I have this is my one implicant, right, because it is covering these two, and then I have another implicant like this, right. Now, these two are basically essential implicant because they are covering some min term which is not covered by any other min term. So, they are called essential prime implicant, right, because so they are called essential implicant. And now, since this is not prime, because I can have a bigger implement there, but that is essential is in the sense that you have some implicant which is covering some min term which is not covered by somebody else, right. That is what is called essential prime implicant. So, what is the objective, as I mentioned here, I mean earlier also, that we have those min terms, right. We try to find out those implicant which actually cover more than one min terms, and we try to grow it and try to find the prime implicant, right, because those prime implicant is the biggest cover, right, because that is covering maximum number of min terms, and I cannot go it further, right. So, our objective is try to find out those minimum set of such cover that is covering all the min terms, and so that I can represent that particular function using those prime implicant only, right. And that is what is the objective of this two level minimization, that you try to find out the minimum cover which is the least number of cube, right. So, that is the number of cube which is covering all the number of product term, right. That is what is called cover minimization. And what is why this is important, you understand that suppose I have this 4 value, right, whatever I just told you. So, this 4 value is nothing but if you just write my f is this, right. So, this is basically x 1 bar, x 2 bar, x 3 bar, right. This is basically x 1 bar, this is x 2 because that is 1, x 2 1, and x 3 bar, right, x 3 bar, and this is basically x 1 bar, x 2 bar, x 3 bar, this is x 3, sorry, and this is basically x 1 bar, x 2 and x 3, right. This is what is x 3. So, these 4 these 4 min terms are this function. Now, if you find a prime implicant which is covering all of them, right. So, whatever I found it. So, then this is just my f is become x 1 bar, right, that is what I got it, right. This is my x 1 bar. So, you understand this prime implicant now instead of, so you can, if you have a circuit which is covering, so I have AND gate for this, I have AND gate for this, I have AND gate for this, and I have AND gate for this, and there is OR gate. So, there are 4 AND gate plus OR gate, but this function can be represented by just x 1 bar, which is nothing but this single line, right. So, that is what is the advantage, right. So, if we just try to find out the prime implicant, that is the kind of a maximum possible size which is required minimum number of gate to implement, right. And then we try to cover all the min terms using those prime implicant, and that will actually have the as a kind of minimum possible way of representing that particular function, or in other way this is the optimal representation of that particular function in sum of product form, right. So, that is how we used to do here, right. So, that is what is the objective of this two level implementation, right. So, this is what is talked about here, that this prime implicant. So, this is given by this Swayam theorem that Boolean function can be implemented only using the prime implicant, right. That is what I just talked about, and the number of such implicant is minimum. So, we can always have a minimum number of prime implicant that can represent a Boolean function, right. That is what is going to, we are going to do it, right. So, what is irredundant? Irredundant cube is something which is basically, if I remove this particular cube, some of the min term will be uncovered. For example, here I have say 3 min term, which this is BC, this is AC, and this is say AB, and these 4 are the on terms. And if I just remove this particular AB, then what will happen? This remain uncovered, right, because now this min term is not covered. So, this particular AB is a irredundant cover, because I cannot remove this particular cube, because if I remove it, some of the min term will be uncovered. So, in that sense there might be some cube which is can be irredundant. For example, suppose you have say if I just take another example, suppose this is my so this is my one of the cover as I given here, and you can have also another. So this is say they say this is also. So if you just think about this, so there is another on node here, and this is another cover, and this is another cover, right. Now you can see. So this is kind of redundant cover, because this is not required, right. Even if you do not have this particular cover, I am actually covering all the nodes. So this is covering this 2, this 2 is covering by this 2, this 2 is covering by this 2, and this node the meantime is covering by this 2. If I just add this, is just a redundant one. So I can remove this one. So this is called redundant cover, but other 3 are irredundant, because they are necessary. If you just remove them, your all the min terms will not be covered, right. This is what is all about, right. So what is essential prime implicant? As I already mentioned that this is not covered by any other prime implicant. So if you just think about this 2 level logic optimization, we can have different kind of methodology. One is kind of this Carnot map, right. We represent the variables. So for example, here the onset consists only these are the onset, right. So this are the onset, other are zeros, right. So they do not occur here. Now our objective is to do this prime implicant of finding. So in hypergraph we have done that. In Carnot map, what is just to try to find out the prime implicant is the same. We try to find out the big such q which represent this, right. So this is 1 and this is 1, right. This is what is the implicant, right. So I have, if you just think about this implicant, I have this implicant 1 which is this, and this implicant 2 is covering 2, 6, 4, 18. This is 2, 6, 4, 10. So this is my implicant 2 and this is my implicant 1. And if we just think about another implicant, for example, say this I just take this 4 corner 1. So this will become another implicant, right, and this is covering this 0, this is 0, 2, 10 and 8. So this is kind of a non-essential implicant, but these 2 are essential implicant, right. So this is in Carnot map also we try to find out those implicant effectively, this prime implicant which is basically covering all the on terms, right. This is how this this happens. So we do not talk about don't care yet. So don't care is something which that particular input combination never occurs, right. We assume that particular scenario will never occur of input, right. So that means those input is invalid. So that is why they are called don't care. So what we can do is, since we know that particular this input combination will never occur, we may take those advantage. We take those particular don't care term, we say them there don't care, because we don't care about those input, and we can use those don't care to optimize further your logic circuit, right, because the assumption is that particular combination never happen. So even if we take them, there is no when you optimize our circuit using those don't cares, it does not matter, right, because so this is how we just use the don't care is represented by x, right. So for example, here I just give an example. So this is my onset 1 and these are the onset, and if I just represent this function and this say these are the x are the don't care, right. So what we can do, so this is my 1 prime implicant that is covering 4, and if I do not compare this don't care, I have only this is another cover, right. So if I just represent this is basically yz. If I just do not take this, so my f will be yz, and this is basically w bar, x bar and z, right. So this is my representation of this function. But if I take this to don't care, I can reduce it further, right. So my representation will be now this yz and this is w bar x bar. So I have reduced it further, because one literal is removed from here, right. So this is how we try to utilize the don't care. So the advantage of this don't care is that we may take this terms to find a bigger cover, or we may not take this, but onset is the mandatory thing. We have to find a cover which will cover all the onset, right. Don't care, based on our requirement we might take it or may not take it, and because of don't care we might have a different solution also, right. For example, if I consider, because I have to cover this to 1, right. So I can cover this way or I can cover this way also, right, because that is also same, then I have a different solution. These two are different, but we can have both the solution are kind of optimum, right. So this is how we actually use the don't care in our Boolean functionality, right. Now I will move on to this discussion of this 2 level logic optimization. So what we have understand that is basically 2 level logic optimization is nothing but try to find the prime implicant of an Boolean function, and you then try to cover those prime implicant, I mean basically try to cover all the min terms using minimum number of such covers, right. So, basically this prime implicant is covering some of them, we try to find out the minimum number of such prime implicant which cover all the min terms, right. And we have lot of various method. What is very well known is Karnaugh map based method. We have this Quine-McCloskey based method. This Karnaugh map is kind of mapping a table, and we try to expand, try to find out the prime implicant on the table, right. And on this Quine-McCloskey is also kind of a tabular method, where you have this in each iteration, successive iteration, we try to find out the implicant, we try to find out the common part of two product term, and we try to find the implicant and we move on, right. So, we know those method, we are not going to detail discussing on those. What I am going to talk about this in this lecture is something that heuristic based approach, right, what is called espresso. Because the problem is this Karnaugh map based method or Quine-McCloskey method, they are not scalable. They are, if the number of input is very small, say 2, 4, 10 till 10, that is fine. Because if you just think about a table size where you have 10 input means 2 to the power n number of entries, right, and now handling that is very difficult, and it is very difficult to visualize as well. So, on the other hand, in espresso, I mean heuristic based approach, it does not always give you the exact solution, which is the fact for this Karnaugh map based method or Quine-McCloskey based method, where we always get the whatever the solution we get, that is the optimum one. But espresso will always give you near optimal solution, but they are very fast, they are scalable, and that is also any time. In any time if you stop, we have a solution, right. That may not be optimal one, but we have a solution to that problem. So, that is why this espresso is kind of the most widely used, I mean algorithm for this 2 level logic minimization. So, instead of going into this Karnaugh map based or Quine-McCloskey method, we will just try to discuss espresso in this discussion. Okay. So, espresso is based on simulated annealing based method. What is simulated annealing based method? It is basically, instead of finding local minimum, we try to find out the global minimum here. So, for example, if you just look into this, if you just take start from some point, right, and you have some optimization function, we will move on and we will find out this minimum, right, because this is a convex, we cannot go out of it, right, because this it will stop here. But if we just start, but maybe this is the local minimum, the actual global minimum is somewhere else. But if I start from some node, I will always stop here, any point here I will stop here. But if I start from some other node, I will go to this, right. So, simulated annealing method is actually doing this. So, it is basically we will start from some point, we try to find out some global local minimum, then we will arbitrarily move on to some other starting point and then try to get the optimization function, right. And this way there is a very high chance that we always, I mean always go into that global optimum one, right. So, we may not go into it, because if my choice of input is not really random, if we do not find any point in this part, then I will not be able to get this minimum. But if we just take really random, I mean starting points, we might most of the time we get this global minimum, right. That is what is that simulated annealing method all about. So, in espresso what we start from some initial cover, because the objective is again different, I mean same, right. We have set of min terms, we try to find out the cover that will cover, I mean basically the prime implicant, which will cover all the min terms, right. So, we will take any starting point. So, maybe all the min terms, right. So, in the initial starting point, maybe all the min term itself is the cover, right, because we just consider all the onset, that is the cover of that. Then we try to update that cover in each iteration, right. So, what we do, we have some operation called reduce, expand and redundant. We will just apply those operations in iterative way, and we try to update this cover, right, and then we try to get some cover, right. So, when we do not have any other option, we do not have any improvement in this, then what we will do? We will do some arbitrary change in this cover and try to find out another initial cover, from where again we will do the same thing, right. That is the simulated annealing part, right, part of part. So, what I am going to do is I am starting from the basic idea that I am taking from an initial solution. We apply certain kind of operations iteratively, unless I reach a saturation point in the sense I cannot have a further improvement over the previous solutions, then I will stop there, because that is the best solution for now, and then I will randomly choose another starting point and then I will keep doing this. Either I timed out or I am happy with my solution, right. That is how this whole thing goes on, right. So, the this primary operation is expand. So, expand is, as I mentioned, that we have some cube which is covering all the minterms, and we try to expand this cube sub cubes as large as possible without covering a point in the offset, because offset is those term which do not cover, right. So, that means it is taking advantage of the other sub cubes, that means the other onset or some do not care set, right. You try to starting from some some initial sub cubes, you try to expand it as far as possible, just to covering the neighboring cubes or minterms or some do not care set, right, and this is how the expand happen. Right. There is an example here, suppose initially my cover is all this 5, right, this 5 at the onset, I am starting from this. So, my initial cover has these 5 nodes, right, and then I try to expand it. If I expand, I just try to cover this 2, right. Now, I have only this is one cover, and then I try to expand from this node, I cover this way, I will get this, right, I got this 2, right. Similarly, I starting from this node, I try to expand this way, I got this. So, I have 3 expanded cover now. Again, I can expand further and I get this is as a cover, right. So, now I have only 2 cover, this is a prime implicant, this is another cover which is covering all the minterms. You can understand here the direction may be different, right. So, from here I may go this way to cover this, or may I go this way and I can take this kind of cover just to cover these 2, right. So, the direction can be different and the choice is not unique, right. So, that is the idea. So, if you just start from here, if you just expand one direction, you will get some solution, that may not be the best solution, right. So, then what you should do, you try to expand it in other direction as well. So, for that we have another operation is called reduce. So, what is that? We have some set of covers, set of cubes that is covering all the minterms, it is just the reverse of the expand operation, right. So, instead of expanding, now I am reducing to some smaller sub cubes. The advantage here is that now if you have a smaller cube, if I just again apply this expand, now I am going to grow in the other direction, whatever just explained here, right, that so from here I expanded this way and I stop here. Maybe this is not the ideal example, but in some scenario maybe this is not give you the good solution, but if you expand this way, you will probably get a better solution, right. So, that is something is the reduce talks about. So, basically reduce, what is that? It starts from some cover, it reduce the size, so that there may be this allow the newly formed cubes by expanding them in the other direction, right. So, that will give you the advantage. So, it is example. So, initially suppose I have this 3 cube which is covering all the minterms, then I reduce it. So, I reduce it, I just got this one, right, and this. Then I reduce this, then I can apply the expand again, so that I am covering these 2, right. So, this is just to say that you can actually have a reduction followed by expansion, which will can give you some different cover, which is a better cover of the minterms, right. That is what is called reduce. We have another operation is called redundant. As I mentioned earlier, that there are some implicant, prime implicant which is essential, that means that is covering some cube or say some minterm which is not covered by somebody else, right. So, there may be some implicant or say prime implicant which is covering some nodes which is already covered by somebody else. So, that is kind of a redundant one. So, it is basically throughout the redundant cubes. For example, here I have this say 4 cube covering all these 5 minterms. You can see here this is already covering this 2, right. This is also covering this 2, right, and this is covering this 2. So, in that sense this particular cover is redundant, right. This is not required, because this is covering these 2 minterms which is already covered by somebody else. This is covered by this is covered by this. So, I should remove this. So, this is what is the redundant done, right. So, from this 4 cover I will, so there are 1, 2, 3, 4, I will end up in this 3, right, this 3 which is covering all the minterms. So, this is what is called redundant. So, what it does, this espresso, it is basically taking advantage of these 3 particular operations iteratively, right. So, it starts from this onset is that minterm, that is I mean that actually whenever there is on, I mean they are 1, then the function will be 1. Offset means they are always 0, when the function is 1 they are 0, and do not care, as I mentioned, they may not, they will not never occur, but I can take advantage of this do not care set, right. So, then what it does, it try to expand, because initially it covered is all the onset, as I mentioned, all the minterms are my cover, initial cover, right. Then I try to expand it, expanding through this onset and the do not care set as much as possible. So, that I will get bigger cover or kind of prime implicant, right. Then I will just do this E redundant to throw out the redundant cubes, right. Then I get some kind of essential cube which is covering all my minterms, right. Then in the loop, what I am doing in this loop, I am going to do this operation reduce. I will just try to reduce it just to go in other direction, then I will expand again, then I will throw out the redundant one. This I am going to do it iteratively unless my cost is stable. Stable in the sense between two successive iteration I do not have any further improvement. So, if I found a scenario and there are between two successive iteration of this loop, I do not have further improvement, that means I got a saturation point, then I will stop. So, whatever the solution I got is kind of best solution for the direction I have expanded, right. So, that direction I have covering that things, right. Then this come the simulation analytic part. Now, I am going to do this reduce gaps, which is basically try to find out some other starting point. I will talk about that, and then I will effectively expand and then redundant. So, I will try to create some another cover which is completely orthogonal to the current cover. Then again I will go back to this and I will do the same way, right. Again I am going to expand, reduce, expand, redundant. So, I am going to do these things, right. I am going to stop it when my time is off or I am satisfied with some results, right. That is what is talk about. So, what is this reduce gaps? Is talking about that for each cube in F, add those subcubes of cubes that are not covered by somebody else, right, some other cubes. For example, here, so I have this 2 cube, right. So, now I will find this minterm which is not covered by anybody, only this, and for this no minterm is covered by only this, nobody else, right. So, I am going to add these 2 minterms as the cover, right. I am going to put this as the subcubes in the in my cover, right. Instead of putting these 2, I am now putting these 2, right, because from there I can actually do this expansion again, right. So, I just try to expand from here, I will get this, right, and so on. So, this is what is talking. It uses D to ensure that new subcubes are not produced just some for some just DC nodes. So, basically we will start from any other minterms and try to grow it in other way, right. So, this is what is that reduce gaps is all about, and then we just add subcubes and add them when they if they cover other cube, right. This is just normal expand operation, and then I can use this E redundant to remove the things. So, this is all about this espresso. It is basically heuristic. You try to explore all directions, all directions. One direction you get a best solution, then you try to reduce it, try to explore the other directions, and this way this particular loop will the inner loop will give you after some iteration that the best solution in this from this initial starting point. Then we just perturb the solution, that means we just try to find out some other initial cover which will cover all the minterms, and from there again I am trying to do this expand reduce the steps, right. So, that I can actually go for some other global minimum, right. That is what is the espresso all about. And I mentioned here that your Boolean function is represented by a hypergraph. Here I have shown this in hypergraph where there are 3 variable. Now, the question is how we represent a hypergraph with 4 variable, right. So, that is nothing but we take 2 such hypergraph of 3 and then I connect the nodes which have a difference of 1 bit, right. Then I just connect them accordingly, right. So, then it will give a 4 when a hypergraph of size 4. Similarly, if I take 2 hypergraph of size 4, I can connect the node which have only 1 bit difference, then it will give a hypergraph of 5 and so on. So, this way I can represent my function in the hypergraph, and this reduce, expansion and redundant and this expand will occur as I discuss here. So, this is how this espresso works, right. So, this is already discussed. So, here is the saturation point. I have an example. Suppose I have initially have these 3 minterms, I expand this way. So, I got this is a minterm, this is a minterm. After that I do the redundant, there is no redundant here, so all are important essential prime implicant. So, this is my current one, then I reduce it again, right. So, I reduce, so I say this will become this, I remove one of them and this is it, again I am expanding. So, I am getting this. So, now you see this and this is the same solution, right. If I just do this redundant, I got this which is same as this. So, between 2 successive iterations I found there is no improvement, right. So, I will stop here. This is how this inner loop works, right, this inner loop. And then I will probably start from some other starting point, as I mentioned, I probably start from this starting point and I will move again. So, that is that second part, right. How this will give you improvements? Here is an example. So, suppose my one solution give you this, right. So, this is my initial cover, right, this 4, and then I just reduce it. So, I just remove some of them. So, I end up in, I have this, I just reduce this one and this one. So, my reduction is this now, right, this I cover only these two, this and these 2 nodes. Then again I expand this way, I got a expand in right direction, because just to cover these 4 terms, this is the optimal redundant set of covers, right. So, I am having 3 now. So, initially I have 4 q which is covering all the min terms, now I have this 3 which is the optimal one. So, this is how this will work, right. So, if you have an initial cover which is not optimal, but if you reduce and expand, you in some iteration you might expand in right direction, and that will give you the optimal solution. Just to conclude on espresso, is basically successfully generates new covers until no further improvement is possible, and it kind of give you near optimal solution, right. It always try to give you near optimal solution, and this is used for primarily for PLA or minimization. And the biggest advantage of this espresso is that it is very much scalable, and it works for very large circuit, which is contrary to the other conventional exact approach like Carnot map or say Quinn-McCloskey. Those are not kind of scalable, right. So, this espresso actually works for bigger circuits and practical circuits. Okay. So, I will now move on to this multi-level logic optimizations. As I mentioned, this 2-level logic optimization is not sometimes is a correct way of representing your circuit, because sometimes what happened that this is too big, right, it is not representable, as I mentioned already. So, in practical our Boolean circuits are represented as a multi-level implementation. We have a multi-level implementation of the logic circuits. So, now how we optimize those multi-level circuit, right, that is what is we are going to discuss now. So, multi-level logic optimization, input is set of Boolean expressions, you understand. So, we have set of Boolean expressions, and our output will be a set of optimized Boolean expressions, right. And our objective is try to here the objective is try to do some network of transformation, right, some transformation of the circuit which is result in some optimized Boolean expression, right. And one of the most common approach is that eliminate common sub expression, because the common sub expression is something and sub part of the circuit which is reused in both 2 component of the function, right. If we find out those common sub expression and you reuse it, then it will reduce the overall size, right. We can have other objectives optimization like elimination, decomposition, simplification and substitution. We can always have some rules for that. We can always try to find out some some way to just redo this, simplify some circuit, some we substitute some complex part by a simpler one, and so on. So, but primarily when you talk about this multi-level logic optimization, we primarily talk about identifying the common sub expressions between 2 expressions and then eliminate them, right. That will give you a big boost, I mean optimize your circuit by large, right. For example, here you take this example. So, I have lot of variables, right. So, these are various variable which is updating here, and this is kind of a network representation for that, right. So, we have this inputs and this is kind of the dependence we have, right. This is actually representing this circuit. Now, if you look into this that common sub expression, for example, this P, right. So, here if you just P, I have this this is I can represent E into C plus D, right, and this T if I represent here, I have this, you can see here A into C plus D and then B into C plus D, right, plus E. So, I can represent this equivalently A plus B into C plus D plus E, right. This is how we represent this T. So, you can see here this is the common sub expression, right. So, this common sub expression I can compute it. So, I am computing this again here and here. So, this is actually giving some extra I mean unnecessary the double computation of the same thing, right. So, what I can do here from this circuit I can make it this, so that I can compute this C plus D as I mentioned here once, and then I can use this C plus to compute this P as I shown here. The same thing is written here. I am using this to compute this P and I am using this to compute the T as well, right. So, this is what I have done here. So, now you can understand that the complexity of this node versus this node is simpler, right. So, this is how I actually can optimize your circuit. So, in multi-level optimization we primarily try to find out this kind of common sub expression between multiple expressions, and we try to remove them. I am going to use one expression, I am going to reuse it, right. That is the kind of optimization we try to do it here. So, the question is here is that how we can do that, right, how we can do this kind of things, right. So, and when engineering we can have other transformation as well. So, there are two kind of approach. One is kind of say algorithmic approach. Algorithmic approach, what it does, it try to find some algorithm for, have some algorithm for each transformation, right, one for common sub expression, one for say simplification, one for say decompositions and all, and then you try to find out those detects those transformations can be applied, where it can be applied, and it keep doing that, right, and when there is no it will stop when there is no way to apply those transformations, right. And in the rule based approach is basically we have set of rules. So, this is the input pattern and corresponding this is the optimized pattern, and we try to find out some pattern matching thing, right. We try to find out those patterns in your design, and it will replace by that the optimized version, right. This is how we can do this rule based approach, and we can have these patterns, the optimized pattern for each kind of transformation as well, right. This is the way we usually do this algorithmic approach and rule based approach. And on the other hand, we usually think about our circuit represented as a Boolean circuit, as I mentioned for espresso also, right, everything is Boolean, right. I have a variable, complement of a variable, and we do all these rules, De Morgan's law, all the rule of Boolean arithmetic we apply, right. There is another way of doing it, like is algebraic model. We might assume this Boolean formula is algebraic formula, right. So, what I am doing here, instead of representing this Boolean function by algebraic expression, all the variable become algebraic variable. Now, I can apply the rules of the algebra, right, algebraic transformation we can apply on that to do this, and that is what is called algebraic model, and that is most I mean one convenient way to do this multi-level logic optimizations, right. I am going to talk about that, right, just to give an elaborate this. So, for example, in this algebraic model I will apply the distributive law of this algebra, right, but I cannot use this De Morgan's law. This is what is equal in Boolean, but this is not equal in De Morgan, I mean in for algebra, right. When this a, b, c are all are basically algebraic variable, not the Boolean variable, then this is not true. For example, this E and E dash, which is basically complement, right, and I can have some property, right, E into E dash is always 0, E plus E dash is always 1, but those are not applicable for algebraic model, right, because here this E and E dash are two different variable, they are not considered to be a complement to each other. So, these are the kind of restrictions are there, but if we just assume my all these expressions are some algebraic expression, then we can actually use the optimizations or the properties of the algebraic expressions, and we can actually do some simplifications. So, one of the so basically idea is that we have set up the sum of product expressions, and then we want to find common sub expressions as possible, and then this we try to find out this common common sub expression between these expressions, right, using algebraic model. And now the question is where to search this common sub expression, right. This is in using the division algorithm, right. So, divisor in the common divisor of two expression. Just to illustrate this, suppose I have this division, this is basically suppose I am dividing this f, which is basically my dividend, this is my divisor, and this is the result, mean quotient, and this is my remainder. So, my f is basically d into q into r, right. Now, if you just think about my f is this, right, ab plus ad plus bc plus bd plus e, I can represent this d, say d is my a plus b, right, and then I can represent this this equivalent to this, right. So, now you can see here this my quotient will be c plus d, right, this is my c plus d, this is a plus b, and the remainder will be this e, right. So, now I can I just apply this division operation on this Boolean expression, right. Now, this is my quotient, this is my divisor, and this is my remainder, right. Now, the question here is that how to apply this division algorithm just to find out the common sub expression, right. So, the question is that the common divisor. So, if these two particular expression has some common divisor, then that is the common sub expression, right. So, for example, here suppose my f1 is this c plus d, which is nothing but e into c plus d, and f2 is the same earlier one. So, which is represented by this. So, you can see this c plus d is the common divisor, right. This is the common divisor. So, this is something is my common sub expression. So, if I can found such common divisor, then I can rewrite my expression like this, f 3 is c plus d, and I can rewrite f 1 is e into f 3 and f 2 is f 3 into a plus b into e, right. So, this is what is all about. So, this is the same as whatever the example I have shown here, right. So, this is what the same thing is happening here. So, the idea is that I am going to use this divisor property, this division algorithm on this Boolean expression, which is considered as the algebraic expression now, and we try to find out this common sub expression elements. I mean common sub expression as the common divisor here. That is the overall approach here. I mean, this is how I am going to do it. Just to go into more detail. So, our objective is to look for common divisor between two expressions, right. Now, question is that where to look for this divisor, right, because we have two formula now, right. So, we have just two formulas. Now, where to look for this common divisor, where to look for this divisor for a function, right. The answer is in the kernel of a function. Right? Now, the question is what is kernel. So, kernel is defined as a cube free quotient of k obtained by algebraically dividing a by a single cube, right, which is called co-kernel. Not clear. So, we will just talk about this in detail. So, as I mentioned here that I can actually do this operation. So, this is my divisor, sorry, this is my divisor, this is my, this is divisor, this is dividend, this is quotient and this is remainder, right. So, now my if this C is a single cube, right. So, which is like ABC, AD, EFG, it is not some expression, right, it is a single cube. So, if I divide this by this single cube and if I get some result, the quotient, if the quotient is cube free, right, then this is a kernel. So, this K is a kernel if this is a cube free. Now, the question is what is cube free, that you should understand, right. So, the idea is that something is cube free which does not have any cofactor, we cannot factor it further, right. For example, suppose we have this is not a cube, this is not a cube free because this I can write like this, right. So, I can write this as a into c plus d plus b into c plus d, which is equivalent to a plus b into c plus d. So, I have a factor c plus d of this, right. So, this is not a cube free, but this is cube free because I cannot represent, I cannot find a cofactor of this, I cannot rewrite this expression in such form that I can find such cofactor, then this is cube free, right. So, if you coming back to this, so that means if you have a expression, this is my expression, f is my expression, right, this is my expression, I divide this by some single cube, not by multiple cubes. So, cube means basically product of those literals, right, that you already discussed. So, single cube means we have only one product term here. So, if I divide this particular function by some single cube by a product term, whatever the quotient I am going to get it, if that particular quotient does not have any other factor, we cannot factor it some sub expression from that, then that particular quotient is kernel, right. So, that is what is called kernel. So, the answer I just talked about this is that algebraically divide the function by co-kernel, this single cube is the co-kernel, and if this k is a kernel, then that is particular the place where should we look into this, right. That is what is I just talked about here, right, that the algebraic divide answer is in the kernel of k. But how it important, I will just talk about this. Before that, I will explain example this kernel further, right. So, suppose A is my expression, is it kernel? No, because it has all a common divisor cofactor 1. So, this is not a cube free. Is this cube free? This is cube free because there is no other factor here, right. This is cube free. This is cube free, this expression? No, because I have a common cofactor here A. So, I can represent this by this. So, this is not a cube free expression. Is this cube free? You can understand this is no, there is a common factor here, right. So, I can represent this by this. So, this is not cube free, but this is cube free because there is no way I can represent this like this, right. So, this is cube free. So, this and this is a cube free expression here, others are not, right. So, when the idea is here, when you divide this function by a single cube and then whatever the quotient you get, you try to find out whether this is kernel or not, right. If it is not a kernel, then we there is no common divisor, but if there is a kernel means there is no common divisor there. So, that is a kind of a unique expression, and then we should look for the common sub expression in that kernel itself, right. Just to go further here, the idea is that you might have a multiple kernels, right. So, the idea is here that you take that function, you try to find out all the kernels, right. For example, here and that means you try to divide that particular function by all product terms, right, all single cube, all the product terms of the input variable. So, I divide this by 1. So, this is not obviously not kernel, because this have B has, because you have B is all common. So, this is B has cofactor. So, then if I divide this by A, this is my quotient, right, but again this is not kernel as I discussed here, right. So, because it has this A as the cofactor. So, this is not a kernel, right. So, similarly here, so this is B is a factor here. So, now if I just divide it by B, I got this is as the quotient and this is a kernel, because this does not have any, this is cube free. So, this is a cube free, that means a kernel. Similarly, if I divide this by AB, I will get CD as the quotient and this is obviously a cube free. So, this way if I just apply this divide this particular function by multiple such single cube, then I will get some quotient and I will just check whether they are cube free or not, whether they are kernel or not. If they are kernels, so I will find out all these kernels, right. Once I have all these kernels, right, then what we can do, because I now this is only for one function, right, I have now multiple such functions, and what I can do, that is given by this theorem, Brayton and Macmillan theorem, right. That is important, because now when you try to find out this common subexpression between two functions, that this theorem says that you should always look into the intersection of these kernels, right. But it says that for expression f and g have common divisor d, if and only if they are kernels, there are kernels this and this, in their kernel this k is the kernel of f, all the kernels of f, and k g is the kernel of all the kernels of g. So, then you d must be in the intersection of this k 1 and k 2, right, and d is an expression of at least 2 cube, right, 2 cube, and there are 2 product term at least on that. So, what is the importance of this theorem is that interpretations, or the importance of that theorem is that whenever you try to find out the common subexpression between this function, you find out all the kernels of these two function, and then you take the intersection, right. If there are some common subexpression exist, that must exist in that interaction only, right. If there is no common subexpression between these two function, there is no, then if it is not there in the their intersection of kernels, there is no other, right, that is the important, right. So, the idea is that to find common subdivisor of two subexpression, the only place to look into is that is intersection of kernel, right. If that particular intersection does not have any common divisor, that means there is no other, right. That is actually give you some algorithmic approach now. So, you can understand that now I got a algorithmic approach to find out the common divisor using this division algorithm, find out the common subexpression of those two functions, right, which is talked about this, right. So, you find, so if you have two functions say f and g, the steps is like that. So, you find all the kernels of f and g. So, if suppose for f 1 you got this k 1, k 2, k 3, all the kernels here, right, and then for g you get say this 4 kernels, right. Then you take this intersection of these two kernel, where at least you should have 2 cubes, because there is another restriction that it must be of 2 cube, right. So, you find, so for example, say this k 1 or k 8 has the only kernel where this has more than 2 cubes, and then you find out the multi-cube common divisor, right, from this k 1 and k 8, right. That is, you extract the multi-cube common divisor of d from this intersection, right, and then you can rewrite these two using this common divisor, and that is d is your common divisor now, right. Just to elaborate it further, suppose you have this f is basically this. So, for example, this kernel 1 you can represent, because you are dividing this f by q 1. So, you can rewrite f by this, g by this, and then this kernel 1 has some common subexpression, right, that is what is the point, right. So, this is the kernel 1 and kernel 2 is that intersection which is talked about, right. So, suppose this is k 1 and k 2, and then I can rewrite this by x 1, because that is the common subexpression part in the kernel. So, I can rewrite this kernel 1 by this, some other stuff is there, some other subexpressions, and this kernel 2 is, this is the common part and this is the other part, right. Now, what I can do, I can just find out this is this q 1 into this plus q 1 into the other stuff, and I can rewrite this by this, right. Then what is happening, this x plus y is the common divisor part, right. Then I can have, this is my common divisor, which is part of the kernel and which is have at least 2 cube. So, this is the kernel, I found it. I can rewrite my function in this form, right. So, d is x plus y, f 1 is q 1 into d plus the other things, g is q 2 into d into this, right. So, just to give an example, suppose my f and g is this. So, I found all the kernels. So, this is these are the kernels of f, right, and these are the kernels of g. So, I can apply the other algorithm just to find out the kernels. Now, we try to find out the kernels within the intersection, right. So, intersection I have this, right. So, if I just do this, if you take this and this, intersection of these two will give you this a plus b, which is basically have more than 2 terms, at least 2 terms. So, this is a multi-cube. So, this a plus b is a common divisor of this, right. So, I can rewrite this expression using this already I have written. So, a plus b, right. So, this is a plus b into e plus this is the other stuff and this is the remainder c d e plus a b, right. So, this is my common divisor and this I can rewrite like this, g equal to I can do this this e into a plus b plus a d plus b c. So, this is my common terms, right. I can replace this a and this by some expression, say d equal to a plus b, and I can just do it d here, right. This is what I am doing. So, this is how the whole thing works, right. So, just to summarize, you just try to find out the kernels, that means you divide those two function using single cube, single product terms, you find out the dividend and you see whether that is kernel cube free or not. That means, then that is a kernel, you find out all the kernels of two function and then you take the intersection of the kernel and you find out those intersection some sub expression which is basically have more than 2 cubes, right, and that is your common sub expression, right. This is how we can do this whole algorithm. Now, the question is here how to find the kernels of an A, right, that is something we have not discussed. The naive approach is something you divide this d by all possible product term, right, because that is the power set of input, right, because this is a single cube I am going to talk about only that single product, right, is it is not the multiple product, right. And then I can, whenever I found some kernel which is cube free, I will just take a quotient which is cube free, I can take that, right. On the improvement side, I can actually recursively check if some kernels are the kernel of other, right, subset of other, or I can just see like commutative operator and whether if this a b and b a is in the same kernel. If I found a b, I am not going to explore b a and so on, right. So, this is something you can do. So, this is how I can actually find the kernels, right. This is the overall summary. That this is how actually I can use this division operation just to find out the common sub expression among multiple expressions, right. So, just to summarize in today's discussion, so we have talked about this logic synthesis, and what we have found that logic synthesis is straightforward, but only complicated part is that logic optimization part, which can be technology dependent and technology independent. So, today we have discussed about this independent part. So, we have discussed two strategies like it can be 2 level optimizations or say multi level optimization, and in 2 level we can have exact solution like Carnot map based solution or say this Quine-McCloskey based solution, and we also have heuristic solution like espresso. So, we have discussed espresso in detail, and also for multi level optimizations we can have separate set of rules and we can apply those rules algorithmically or say rule based way. Just to find out some optimum circuit, and we can have 2 different model, Boolean model or algebraic model. So, we have discussed today how we can use this algebraic model just to find out some common sub expression using the division of algorithm between 2 functions, right. And this is how we conclude this discussion. In next discussion, we are going to talk about this this technology dependent logic optimization specifically for FPGAs. Okay. Thank you.